All right, so in the last chapter, we talked about some of the fundamental concepts of radiation. We talked about how when a surface is irradiated with radiation, that radiation can be reflected or it can be absorbed or transmitted. And we talked about how a surface can emit radiation due to its temperature. We talked about the properties of radiation: emissivity, reflectivity, absorptivity, transmissivity. And we talked about diffuse versus spectral emitters and reflectors. In this video, we're going to focus on diffuse emitters and reflectors and how their radiation interacts with the surfaces around them. Makes intuitive sense that radiation heat transfer between two surfaces is going to depend on the orientation of those surfaces in addition to the temperature and properties. Now we're only going to consider surfaces, of course, that emit and reflect radiation evenly in all directions. Thus they're diffuse emitters and reflectors, but we still consider those orientation effects. The view factor is the fraction of radiation that's leaving surface I and hitting surface J. And of course, those values can be anywhere between 0 and 1. Now, your book goes through the derivation of the view factor, which we're not going to go over here, but we will talk about some of the relationships that are suggested by those definitions. You can see that from the definition for the view factors of Fij and Fji, you can see the values of those double integrals are the same for each. So if you combine those two together, you get the reciprocity relationship. And that reciprocity relationship applies to two surfaces. And of course, those are diffuse surfaces. Now let's consider an enclosure. So we can see in 13.2, we have surfaces at different temperatures, all the way up to the nth surface, the temperature of the nth surface, and each of those surfaces have a radiosity of J. Remember that radiosity, it is the rate of the radiation that's leaving the surface, and it's the emitted plus the reflected radiation. So for this case, we need another principle to allow us to relate all the view factors for radiation to and from those surfaces with respect to one another. And the summation rule is what's going to allow us to do that. It says that the sum of all the view factors from surface I within that enclosure to all n surfaces of that enclosure, including itself, have to be equal to 1. So can a view factor accounting for radiation to itself, can we have that? Can we have a view factor for a surface onto itself? And yeah, absolutely, of course. So the fraction of radiation leaving the plane surface in figure A here and hitting itself is 0. Same thing for the concave surface in part in the second in figure B here. But of course, the same thing couldn't be said for the concave surface in figure C. And between those two rules, we'll find that it's necessary to evaluate only 1/2 n times n minus 1 view factors. So if a surface has 6 sides, we'll find that we have to have 36 view factors because each of those 6 surfaces has a view factor onto the other 5 surfaces, and then there's one where you account for the emission onto itself, and that gives us 6 times 6 view factors altogether. So, but we only have to really calculate 15 of those directly. So let's try one of those out. We have 2 spheres, one inside another, 2 surfaces, 1 and 2. So the total number of relationships that I need to derive is just 1. And now let's list those view factors. We have 4. So let's look at the view factor from the inner sphere onto itself. We have a concave surface, so the view factor is 0. And then since the sum of the view factors from a given surface has to equal to 1, we have a view factor for surface 1 onto surface 2 of 1. And now it's time for our reciprocity relationship. We see that we've already figured out that the view factor F12 is 1, so that simplifies things a bit, and then we bring the areas over to one side, and if we know the radii of those 2 spheres, we can calculate the view factor F21. And then finally, we apply our summation rule, which tells us that the sum of the surfaces of the 2 have to be equal to 1, and that gives us the view factor F22. Okay. All right, sometimes that geometry is a little bit complicated, and table 13.1 tabulates the view factors between various 2-dimensional geometries with the figures extending into the page here. And then we also have 3-dimensional geometries, but in this class, we're really predominantly going to be working with geometries in which we can derive the expressions for the view factors ourselves. All right, so let's bring some of those concepts together to calculate the rate of heat transfer between 2 surfaces due to radiation. gets a little bit more complicated when you have surfaces that reflect radiation, and that radiation irradiates another surface, which absorbs some. And we'll assume that we have opaque surfaces where we don't have any transmission. And then some of that, that surface reflects maybe some of that back onto another surface, and that's reflected or absorbed. Well, our analysis gets a lot simpler if we just limit our discussion to black bodies, which, as you recall, are perfect absorbers. So all of the incident radiation is absorbed and not reflected. So we define the net rate of radiation leaving surface I and hitting surface J as the rate of radiation that's leaving the surface minus the rate of radiation coming into the surface from surface J. And we have an expression for that if we have a black body. The fraction of energy emitted by a black body surface I is the view factor times the EB term, so the emitted radiation of a black body. And then we multiply that by the area to get that in terms of watts. And then we subtract the fraction of emitted radiation coming from the surface J going to surface I in the same manner. And then, of course, that reciprocity relationship equates the product of those areas and view factors. And then we can use the Stefan-Boltzmann relationship to define the emitted radiation from a black body. And then that's our equation for the net amount of radiation from black body surface I that hits surface J. And of course, if we have multiple surfaces, or if we have an enclosure, we just sum all the heat transfer rates from surface I going into all of those end surfaces, and then sum them up to get the total heat transfer rate by radiation from that surface. All right, well, I hope that was helpful. See you in class. Let me know if you have any questions.